Hi boys and girls, this video comprises the lecture for section 9.8 entitled Power Series, and it starts on page 659. Now notice in the previous section we discussed the concept of approximating functions by Taylor polynomials. For example, the function f of x equals e to the x can be approximated by its Maclaurin polynomial as follows. This is a Maclaurin expansion, which would mean it's centered at 0. First degree polynomial, second degree, third degree, fourth degree, fifth degree, etc. We saw that the higher the degree of the approximating polynomial, the better the approximation becomes. In the last section, we learned how to generate each of those terms. We knew how to take each derivative as a coefficient, the second derivative over 2 factorial, the third derivative over 3 factorial, times the x term, whether it was the x term centered at 0, which means just x cubed, or if it was centered at some other number, it would be x minus something, quantity cubed, whatever. We learned that generating that polynomial was not just some mathematical exercise. It was actually creating a polynomial that accurately approximated values of the given function. And remember, I said it's pretty amazing that you can get a polynomial function that looks so much like something like an exponential function or a sine curve or a cosine curve. How do polynomials and trigonometric curves connect in that way? It's pretty amazing when you think about it. Now again, we saw that the higher the degree of the approximating polynomial, the better the approximation. I guess if we really wanted to be very, very accurate, we could keep going with the 6th degree polynomial, 7th degree polynomial, 8th degree polynomial. You're probably seeing where this is going. As it happens, we will now see that several types of important functions, including f of x equals e to the x, can be represented exactly by an infinite series called a power series. Now, what we're going to do is we're going to take the idea of the polynomial functions that we had in the last section, and we're going to say no longer will they be limited by some finite sum where we're going to get a 6th degree polynomial or an 18th degree polynomial. No, we're going to take that series and expand it out to infinity. The idea, of course, being that if we actually could expand it to an infinite amount of terms, it would no longer be an approximation, it would be the exact function. For example, the power series representation for e to the x is, here's your expansion, your a sub 0 term, your a sub 1 term, your second degree term, third degree term, etc., etc., etc. And then here's the nth degree term, x to the n over n factorial, but it has plus dot 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 because, of course, it keeps going to infinity. Notice here, and I'm going to change colors to make this point, equals, not approximately equals, e to the x, that function, with all of its strange mystery, is equal to this polynomial function. That's crazy. For each real number x, it can be shown that the infinite series on the right converges to the number e to the x for x equals 1, 2, 3, etc. The following definitions will lay the groundwork for developing these series. So we have definition of power series. If x is a variable, then an infinite series of this form, a sub 0 plus a sub 1x plus a sub 2x squared, a sub 3x cubed. You can see that if it's just x here, that means c is equal to 0. It's centered at 0. And here is your nth term, which will be handy. We'll need that nth term when we're doing things with these power series, plus blah, 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 is called a power series. Probably called a power series. I don't really know why, but maybe I'm guessing because we have variables with powers. These are polynomial terms, or maybe because it's really powerful, or maybe because we feel that the power of mathematics is overtaking the world. I'm not really sure. More generally, an infinite series of this form, notice now we're going to put in x minus c for each of the terms, is called a power series centered at c, where c is a constant. So the general case, x minus some constant, where there's some sort of horizontal shift off the x-axis, as I mentioned in the previous section. And then a more specific case would be when it's centered at 0, No horizontal shift means you wouldn't have to put x minus 0 in there. You can just use x for each term. So are you ready to make some power series? I'll bet you are. Here's example 1. We have actually there's nothing to do here. It's just a demonstration of several power series. The following power series is centered at 0. Now we already know this. If you're wondering, it's always going to be x minus, some number or plus some number to the n power if it's centered anywhere else other than 0. If it's just x to the n, then it's x minus 0 to the n, which means it's centered at 0. And so notice this is your general term, and then as you create these terms, this is what the power series looks like. Here's another power series centered at -1. Remember, since the general form of the power series is x minus c to the n, putting -1 in there gives you this term, x plus 1 to the n power. And it's got a little alternating piece to it, and you can see some terms are generated there. Here's another one centered at 1. These are just some examples of power series. 1 over n, x minus 1 to the n power, because it's centered at 1. Now, what are we going to do with these power series? We're going to talk about the radius and interval of convergence. A power series can be viewed as a function of x. What? Oh, yes, it's true. Let's say f of x equals, again, the sum of all of these terms. If I wrote out all of these terms, I would have a big dang long polynomial, wouldn't I? F of x equals that polynomial. Yes, it's true that there are an infinite number of monomials in that polynomial, but we can still call that a function. And this is sort of the general way of writing it so that we don't have to write out an infinite number of terms. We're saying this term from 0 to infinity, all added up, is equal to this function, which allows us to talk about the domain of our function. It turns out the domain of a power series that's written as a function is the set of all x for which the power series converges. Thank goodness we know how to find out how series converge. Determination of the domain of a power series is the primary concern in this section, and it is something that shows up quite frequently on the AP exam, at least the BC exam. You will be guaranteed at least one question. I don't know if it'll be multiple choice or free response, but you will definitely be discussing radius of convergence and or interval of convergence, so this is an important lesson. Of course, every power series converges at its center C. This is sort of an analytic reason why it converges, because at the center, when C is minus c, if we put c in for x here, c minus c just becomes 0 to the 0 power because you're starting at 0, and that's a 1 times a sub n or a sub 0, and so you end up with, of course, f of c, the function that you're creating, is going to converge at this first term, okay, which is the function value at c. But remember, in general terms, remember when we were first starting to talk about this, some generic curve, and we wanted to create a polynomial approximation, we said the first thing we do is nail it to a specific value on that function. Some x value, and then of course some f of c value, and we started creating our polynomial approximation here. So remember, this would be like 2 terms, and then adding the second derivative would give us concavity, etc., etc., etc. But because we start with a polynomial approximation in an infinite series, which is going to give you the exact value of that function, we started at c by saying we're going to let those function values be the same. So that means, of course, that for every power series, the domain is going to include c, the one spot where you know for sure that it's converging. Now, there could be other spots, but definitely C. Let's expound upon this. So C always lies in the domain of F. The following important theorem states that the domain of a power series can take 3 basic forms. A single point, which would be C, in other words, converging just at the center of the power, at the center, or an interval centered at C, so your C, wherever the polynomial is centered at, and maybe a range of values on either side, or the entire real line. Those are your three options for the domain of a power series. Notice this little diagram demonstrates it. We could simply have one spot of convergence at C. We could have an interval of convergence, C of course, and then some distance on either side, the same distance. We call that distance the radius of convergence. So for example, if I were actually going to, let's just put a little convergence, it's hard for me to spell and talk at the same time. Let's just put a little number line up here, something like, well, let's keep it red. Alrighty, and then let's say maybe this particular polynomial is centered at 2. And we find that R, our radius of convergence, is 3. That means you can go 3 units to the right of 2, 3 units to the left of 2. R is 3. That means you can go in both directions 3 units. Now you can see that if I go 3 units to the right, I'm at 5. 3 units to the left, I'm at -1, which means my interval of convergence is -1, 5. So that's the connection between the interval of convergence, your C, and then of course however many values on either side of it, the radius of convergence, and your radius of convergence, which is simply the distance that you're allowed to go on either side of C. That was the second case, obviously requiring the most explanation. The third case is maybe your series converges on the entire real line. Who knows? That could happen. So these are the 3 cases that you can have. That's it. 1 point, an interval, and then infinity. Everything works. This definition says, restates the following. For a power series centered at C, precisely one of the following is true. The series converges only at C. Or there exists a real number R, which we know is called the radius of convergence, has to be bigger than 0 obviously, such that the series converges absolutely for a range of values on either side, and diverges too, but we're mainly interested in the convergence. And number 3, the series converges absolutely for all x. The number R is the radius of convergence of the power series if it only converges at C, so we can't go anywhere on either side. The radius of convergence is 0. If the series converges for all x, which means we can go far, far on the right and far, far on the left, meaning to positive and negative infinity, the radius of a convergence is infinity. And then the set of all values x for which the power series converges is the interval of convergence. So let's find some of these crazy things. Are you ready? Let's find the radius of convergence for this series. Now PS, and this is an important PS, to determine the radius and convergence of a power series, we're going to be using the ratio test every single time. And the ratio test, if you remember, is basically taking the limit as n approaches infinity of the absolute value of the a sub n plus 1 term, over the a sub n term. And whatever that limit is will tell us something about the convergence of a series. Now, we'll use, of course, the general term of the series. So for this particular example, we're going to take the limit as n approaches infinity of, and since I'm putting the a sub n term on top, it's going to be n plus 1 factorial, and then x to the n plus 1 over the original term, which is n factorial x to the n. Now let's do a little rewriting here so that I can do some canceling. The limit as n approaches infinity, I keep wanting to write b there. And let's rewrite this as n plus 1 times n factorial, and then let's write this as x to the n times x to the 1 over n factorial x to the n. Cancel, 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 cancel. Now what am I left with? I'm left with the limit as n approaches infinity of the absolute value of x times n plus 1. Now I can put that in absolute value as well, but I want to talk about now what we have as our limit. Before, when we were calculating limits, we didn't have x in there. There was no variable in there. It turned out to be like a number, maybe 0 or infinity or 1/2 or something like that. The answer that we got told us whether or not the series converged. Remember, for the ratio test, if your limit is less than 1, we have convergence. If the limit is greater than 1, we have divergence, and remember, if the limit was 1, inconclusive. We couldn't tell anything. But, boys and girls, there was no variable. It was just a number, 0, infinity, whatever, 1/2, and we were able to look at this and decide. Now we have a variable. And so what we're going to do with that variable is it's not going to tell us whether or not it converges or not. We're going to make it converge. But we do have to look at the limit of the n pieces that we have left. Look what happens when I put infinity in for n here. Since it's in the numerator, this is infinity. So we go no further. This diverges because infinity times whatever the x value is, whether it's 1 or 2 or 7, is infinity. So this series diverges. And therefore, it's not going to converge for any other place than the center. At the beginning, it's probably a good idea to write down what the center is. We know the center is 0 here. So that is the only place of convergence for this particular series at 0. So I guess you would write converges at x equals 0. And that's it. All right, are you ready to do some more? Good. We've got a few more examples. Now, just a final note on this. Remember that since it only converges at x equals 0, the radius of convergence is 0. So it did say find the radius of convergence, and so we probably should answer that question. It might show up that way on a test or quiz, or no, I mean the AP exam. All right, so now let's find the radius of convergence for this series. This is kind of fun because we know exactly what to do. We're going to take the limit as n approaches infinity of the absolute value of the a sub n plus 1 term, which is 3x minus 2 to the n plus 1. Remember, it's only the n plus 1 that increases, not the x. And then over the original term, which is 3x minus 2 to the n. Now, before I simplify this a little bit so I can do some canceling, let's just mention here that c is 2. Okay, this is centered at 2. And so we kind of keep the x minus 2 piece intact, right? Because it's centered at 2, and that's sort of the defining principle of this particular series. Just FYI, we'll come back and revisit that topic in a moment. Now, let me go ahead and do a little simplification. I'm going to rewrite x minus 2 to the n plus 1 as x minus 2 to the n, and then x minus 2 to the 1, so that I can cancel this with the x minus 2 to the n in the denominator. Cancel, 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 cancel. Now, boys and girls, we have the limit as n approaches infinity of this term, the absolute value of x minus 2. Now remember, you're not putting infinity in for x, you only put it in for n terms. Well, there aren't any left. And so let's pretend like x minus 2, maybe x is 3, and so what we have here is the number 1. The limit as n approaches infinity of 1 is just 1. So since there's no n terms here, what we actually have as our limit is the absolute value of x minus 2. Now remember, we don't at this point ask whether or not this converges. We say, let's make it converge, because we know by the ratio test that when our limit is less than 1, we have convergence. Remember, our limit has a variable in it. So when we put this less than 1, we're imposing the condition upon which it converges. Now that means if I take the absolute value bars away, first of all, the radius of convergence from our center is 1 unit. We don't change this to an x here when we're determining the radius of convergence. It is 1 on either side of this center, okay? So to actually answer the question, we get radius of convergence is 1. But let me go ahead and expound a little bit and say I can change this absolute value inequality to this. So basically I need to keep x minus 2 between 1 and negative 1, which when I solve for what that actually means for x, I get this. I really need then to have my interval of convergence will be 1 and 3. because 2 is right between them. If you go 1 to the right, you get to 3. If you go 1 to the left, you get to 1. So your interval of convergence is 1, 3. And we'll talk about the endpoints in a moment, but at least you have those numbers. The radius of convergence is 1. Pretty fun, huh? Let's do another one. Radius of convergence of this term, we're going to, first of all, let's rewrite this because it's so confusing, I find, when you have this alternating factor. There's just too much going on. Then I'm going to write this as x to the 2n plus 1 over 2n plus 1 factorial. So here's really our nth term. Now remember, we're going to be finding the limit as n approaches infinity of the absolute value of this term, negative 1 to the n, and then we'll have x to the 2n plus 1 over 2n plus 1 factorial. Now I just want to point out to you that taking the absolute value of this means this guy becomes sort of moot. Remember, he just changes the terms from positive to negative, or vice versa. So taking the absolute value, there will be no negatives. It's only going to be positive. I'm making this distinction right now because when I want to take this limit, I think I'll keep this color, I'm not going to bother with the alternating series term. I'm just going to do this part because it's already confusing enough, and I don't want to do negative 1 to the n plus 1 blah blah blah. It's just a negative or positive number, which when you take the absolute value has no meaning. So numerator will be the a sub n plus 1 term, which will be x to the, if I put 2n plus 1, this becomes 2n plus 2 plus 1, which is x to the 2n plus 3. Over the denominator here, if I put n plus 1 in, I get 2n plus 2 plus 1, which is also 2n plus 3 factorial, over the original function, which is x to the 2n plus 1 over 2n plus 1 factorial. Okay, we got it down there. Let's do some simplifying. The limit as n approaches infinity of, we'll just keep everything in absolute value bars so everyone's all happy with what's going on. Let's rewrite this as x to the 2n plus 1 times x squared, okay, because you would add those exponents to get 2n plus 3, but I want this to match that. So I'm going to put this now over, same thing for this guy. Let's write this as 2n plus 3, 2n plus 2, and then 2n plus 1 factorial, because I want that to match this guy. Because now I'm going to multiply by the reciprocal of that denominator, 2n plus 1 factorial over x to the 2n plus 1. Bam. Cancel, 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 cancel. What do I have left? I have the limit as n approaches infinity of the absolute value of x squared over 2n plus 3, 2n plus 2. Now remember, boys and girls, when we were doing convergence before and we were taking the limit at this point and we were plugging infinity in, we didn't have a variable here. We had a number, like a 1 or a 4 or something like that. But remember, that variable is going to be a number, and whatever number it is, when I plug infinity in for n here and here, it's going to be that number over infinity. 4 over infinity, 9 over infinity, and what is the limit of that term? Of course, it's 0. So what this tells me is that no matter what x is, I have convergence. I have the limit of this term being 0, which tells me that for this series, it's going to converge everywhere. It's not going to converge at, I didn't get an answer like, oh, x minus 3 has to stay less than 1 for this to converge. I got, no matter what x is, because of this, the arrangement of this term, plugging infinity into the denominator, I get convergence. And so for this series, your radius of convergence is infinity, and your interval of convergence would of course be negative infinity to infinity. So we've seen 3 types of convergence for these series. Now, what else are we going to do? We're going to discuss what I mentioned before. endpoint convergence. Note that for a power series whose radius of convergence is a finite number r, the theorem we saw previously says nothing about the convergence at the endpoints of the interval of convergence. Each endpoint must also be tested separately for convergence or divergence. As a result, the interval of convergence of a power series can take any one of the 6 forms below. Now, before I talk about the 6 forms, what they're saying here is what we have done on the previous 3 examples, we're going to do exactly the same thing, except once we get our interval of convergence, we are then going to look at each endpoint to make sure that it converges for the series before we make our final decision. So that means that we could have, again, radius of convergence be 0 if C is the only place where it converges. The radius of convergence could be infinity if the entire real number line is where it converges. And then we could have these 4 scenarios if there is a radius that's something other than 0 or infinity. You could have the interval where both of the endpoints are not included. Perhaps the right one is, or the left one is, or both of them. So when I showed you that interval of convergence before and it was 1, 3 or something, we would need to check 1 and 3 to see if it converges in the series, and you're going to see how this works in just a moment. So these are the 6 possibilities that we could have, because there are 4 different arrangements depending on what the endpoints do. Now it's time to look at some of these examples. Find the interval of convergence for, notice they're not asking for radius anymore, because since they've added on the extra sort of proviso of testing the endpoints, we're going to be able to get the exact interval of convergence. What I was showing you before and calling the interval of convergence wasn't really complete because I hadn't tested the endpoints at that point. But that's what we're going to do now. So, but for the first part of this, exactly the same thing. We need to take the limit as n approaches infinity of the absolute value of the a sub n term, a sub n plus 1 term, x to the n plus 1 over n plus 1 over the original a sub n term. Then do some rearranging. You know the drill. I'll just go through this a little bit more quickly. I'm going to write this as x sub n, x to the n, x to the 1 over n plus 1, and then of course times the reciprocal of my denominator n, x to the n. What I like about this is of course that these x to the n's cancel. Now I have the limit as n approaches infinity of the absolute value of x, and then times this term, n over n plus 1. Now again, this variable here could be a constant. It could be a 2, a 4, a 7, whatever. But I plug infinity in to the n term. However, notice that this is a ratio, a rational expression here, where the degree of the numerator is the same as the degree of the denominator. So the limit of this term is going to be the ratio of the leading coefficients, which is 1. So this limit is actually the absolute value of x times 1, which is simply the absolute value of x. Now remember, we want this series to converge. So we're going to make that happen by saying, well, it has to be less than 1. Because remember, for the ratio test, then your limit has to be less than 1 for convergence. You have a variable, which means you get to define what will make this series converge. Now, what that means is, since this was centered at 0, c equals 0, I probably should have written that down at the beginning, that basically you can rewrite this inequality as -1 less than x less than 1, which gives you this potential interval of convergence, -1 to 1. But of course now we're going to learn what it means to test the endpoints. Change of color. Let's go back to our original term and plug in for x -1. When we do so, this is the series that we are investigating. I'm not going to put the n blah 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 to infinity. We're going to have now -1 to the n over n. If you recall, if I take out the alternating part, this is the alternating harmonic series, which we learned, and you could apply the alternating series test if you want to, but we learned that it converges. Okay? So because when we plugged -1 into that nth term, that original a sub n term, and investigated that resulting series for convergence, and we found that it converges, that means at -1 our original series will also converge. Now let's test 1 by plugging that into the original term. I'm going to now have this series to investigate, 1 to the n power, which of course is just 1 over n. This is the harmonic series, which we know diverges. So what we've discovered here is at this endpoint, no go. So our ultimate interval of convergence here, let's use purple, is going to be yes, include -1, don't include 1. And that's your interval of convergence. Cool. All right, let's do another. I have several examples, which makes for an extra long video, but it also makes for very good explanation of what you need to know. Actually, there's only 8 examples, so we're almost done. Let's find the interval of convergence for this series. First of all, of course, we go to our limit. And remember what I showed you before, and I do tend to over-explain things, but let's go back over here. Since I am taking the limit as n approaches infinity of the absolute value of this. Did I do that on the previous slide? I hope I did. Yep, okay, just checking. Okay, absolute value of this -1 to the n, which alternates the series. Then I'll have x plus 1 to the n over 2 to the n. Well, the absolute value is just going to take the relevance of this term away. Positive, negative, not anymore, not with absolute value bars. So I'm not going to carry that over into my limit, just for the sake of a more organized, clean looking kind of, process. So just so we understand that that's what the absolute value does to that term. Now, my numerator here is going to be the a sub n plus 1 term, which is x plus 1 to the n plus 1 power, over 2 to the n plus 1 power, over the original term, which is x plus 1 to the n over 2 to the n. There you have it. And now let's simplify a little bit. N approaches infinity. You'll probably get to the point where you go straight to this step, actually, and maybe this step as well. X plus 1 to the n times x plus 1 to the 1 over 2 to the n times 2 to the 1, so that it will cancel now with our original series, 2 to the n over x plus 1 to the n. Of course, you have to multiply by the reciprocal of that. These cancel, and I end up with the limit as n approaches infinity of this fellow, x plus 1 over 2. Now, I want you to notice something. There's no n in here. So there's nothing to plug infinity in for. Remember, x is standing for some number. What if that was a 7 or an 8? Let's say it's an 8 or something. This limit would be 9/2, and it would diverge. If x was 0, then it would be 1/2, and it would converge. But the point being, this is the limit. So there's no plugging anything in, and since that's the limit, and I want it to converge, I'm going to say then that x plus 1 over, I can do it this way, over 2 has to be less than 1, because by the ratio test, my limit has to be less than 1 to converge. Now, I can also say then, if I just multiply this by 2, I'm going to get x plus 1, the absolute value of x plus 1, has to be less than 2. Now this is important because this defines our radius of convergence. Remember that C was 1 here. So my little sacrosanct term x plus 1 less than 2 tells me that the radius of convergence is 2. But let's expand this a little bit to get the interval of convergence. Now I can write this inequality. -2 less than x plus 1 less than 2 tells me that my interval of convergence can be, if I subtract 1, 1 and -3. So from -3 to 1, and of course this is questionable. We don't know if it's going to include these two endpoints or not. Let's see. Time to change colors. If I take -3 back into the original function, Okay, this gives me negative 3 plus 1, which is negative 2. Let's take a look at this series. Of course, I have that baffling alternating part that just seems to confuzzle everyone. But now when I put negative 3 plus 1 in, I get negative 2 to the n power over 2 to the n. That's interesting because that almost cancels. Well, let's do a little simplification. What if I have negative 1 to the n and I take out the negative 1 to the n that makes that negative, and then just write that as 2 to the n, right? Over 2 to the n. These guys cancel. And then negative 1 to the n squared is negative 1 to the 2n, which when you square this, boys and girls, it doesn't matter what n is, since this is an even number now, I'm basically looking at summing up 1 from 0 to infinity. This, of course, is a divergent series, 1 plus 1 plus 1, etc. So what I have discovered is that at negative 3, I have a divergent series. Now let's test the endpoint at 1. We have here, once again, go back to the original series. You have negative 1 to the n. No problem. I'm going to be okay with that. And then when I put 1 in, I get 1 plus 1, which is 2 to the n, over 2 to the n. Wow, that cancels out right away. But once again, I have negative 1 to the n power also diverges. So, boys and girls, both of the endpoints diverge, which means your ultimate interval of convergence, IOC, is negative 3, 1, with neither endpoint inclusive. One more example like this, and then we'll go to our last little mini topic. Let's do another one. Find the interval of convergence. I do like it when there's no alternating little part, so this is good. We have the limit as n approaches infinity. Let's just cut to the chase. Wanna? Let's make this x to the n plus 1, but let's write it as x to the n times x to the 1 over n squared, and this is really just going to be n plus 1 quantity squared, times the reciprocal of this original term, which is n squared over x to the n. Okay, so I just saved myself a little work by doing that. Now I end up with the limit as n approaches infinity of the absolute value of, I have x, and then it's multiplied by n squared over n plus 1. I'm going to write that in one big parenthesis since they both have the exponent 2. And let's examine what happens as I let this term, the n values, go to infinity. Even if I squared all of this out, you can see that the degree of the numerator and the degree of the denominator are going to be the same. Therefore, we will take the ratio of the leading coefficients, which is 1. So our limit is going to be the absolute value of x times 1, which of course is the absolute value of x. Now, once again, I will decide that I want to keep this convergent. This could be a number like 1 or 2 or 7, but it's a variable. I'm like, hey, I know that if this quantity is less than 1, it will be convergent. Since it's a variable, I can make it convergent by saying, I'm going to keep you less than 1. This means our radius of convergence is 1, because this is centered at 0, c equals 0. And when I make my little inequality, this is what I get. And again, this potential interval, these are just questionable right now. And it's time to test the endpoints to see if this series converges at the endpoints. So let's go back to the original series. If I put negative 1 in for n for x, I get negative 1 to the n power, and I'll just keep that separate. And then that'll be 1 over n squared. Well, this is an alternating series. You would test to see if it converges probably by using the alternating series test. Obviously, you can see the term goes to 0 as you go out to infinity, and then the question would be, is each subsequent term going to be smaller than the first one? Since each time you're going to be increasing the denominator, subsequent terms will be smaller, so this does converge by the AST. Now, it might take you a little longer to work all of that out, but that's what you would need to do. What this does is confirm that -1 is going to be in the interval of convergence. Now we need to check for the other endpoint. Let's take 1 and go plug it back into our original series. 1 to the n power, of course, is just 1 over n squared. Now this is a p-series. A p-series where p is greater than 1 means it converges by the p-series test. So what you have shown is that 1 is also going to be in the interval of convergence. Therefore, your interval of convergence for this series is -1, 1. All right, you guys are getting some good examples and instruction. And if you need to pause the video and go get, a smoothie or whatever and come back, this is probably going to take about 5 more minutes to finish, just to let you know. All right, now look at this topic. Don't be afraid. Differentiation and integration of power series. Are we really going to try to take the derivative and take the integral of power series? Well, what do you think, boys and girls? Isn't that the title of what we see here? But it's not hard. It's really easy. And look at this first sentence. Once you have defined a function with a power series, it is natural to wonder how you can determine the characteristics of the function. Is it continuous? Is it differentiable? And as I typed up this little sentence, I kind of chuckled to myself thinking, natural for who? I'm sure you're thinking, gosh, it's not natural for me. I don't care if you can integrate or derive or if it's continuous, but it is natural for mathematicians, boys and girls. So the following theorem answers these compelling questions. If the function, remember we are defining this infinite series as a function, let's say this is our series, it has a radius of convergence greater than 0, which means basically it's not just converging at C. It's got more things going on, something like this. Then f is differentiable and continuous. Bam, that's it. How easy was that? Moreover, the derivative and antiderivative of f are as follows. F prime of x is the derivative of the nth term. Remember, these are monomials. You're just going to take the derivative of the term using the power rule. So we say n times a sub n, and we subtract 1 from the exponent. That's the derivative. And if you look at individual terms, you're just taking the derivative of individual terms. A sub 0 is a constant, so it's gone. And then the derivative of this, 1 times a to the 1, and then this becomes to the 0 power, so that's just a sub 1. And then 2 times a sub 2, and then this becomes a 1 exponent. That's where this term comes from, etc., etc., etc. So easy. Now look at integrating this term. The integral of f of x, believe it or not, is just integrating each term according to the power rule. Here's the integration of the nth term. We would add 1 to the exponent, n plus 1, and then divide by that new exponent. That's where this term comes from. A sub n is just a coefficient. So in integrating the individual terms, I want you to notice that when a sub 0 was a constant, taking the derivative, of course, gave us 0, but integrating puts the x back on it. But be careful, depending on where the series converges, it actually puts the x minus c term back with the a sub 0 term. So that needs to be taken into account. And then look at the a sub 1 term. We would add 1 to the exponent and then divide by the new, and this would give us x minus c quantity squared over 2, etc., etc., etc. So easy. The radius of convergence of the series obtained by differentiating and integrating of a power series is the same as that of the original power series, which is awesome. So all we need to do is find the radius of convergence for the original series. It will also be the radius of convergence for this guy and this guy. The only thing you have to check is that the interval of convergence might be slightly different because the behavior at the endpoints might be slightly different. So we're going to end this lecture with our final example where we're going to consider the function given by this series. We're going to find the intervals of convergence for the integral of the series, the actual series itself, and the derivative. Let's start with the actual series itself and find out what the potential interval of convergence is. So as usual, we're going to take the limit. Let's do the little shortcut. N approaches infinity of the absolute value of x to the n plus 1, but let's write it as x to the n times x to the 1 so that we can be ready for canceling. And then this is just going to be n plus 1 in the denominator times the reciprocal of the original a sub n term, n over x to the n. Now the x to the n's cancel and you end up with the limit as n approaches infinity of this term. We've got x and then we've got n over n plus 1. We've been here before, right, boys and girls? We can see that when we plug infinity into this term, since the degree of the numerator and denominator are the same, we take the ratio of the leading coefficients, which means we end up with the absolute value of x times 1, which means the limit is the absolute value of x. By the way, I want to keep that convergent, so I'm going to say, hey, let's make u less than 0. That means your radius of convergence is 0 since the series is centered at 0. And setting up my little inequality will be -1 less than x less than 1. So the potential interval of convergence, depending on the endpoints, -1, 1. Let's figure out what's happening at the endpoints in the original series. We have basically when we put -1 in, we get a little alternating factor, and then this becomes 1 over n. This is the alternating harmonic series which converges. So that means this -1 will be in the interval of convergence. Now let's see what happens when we plug 1 into the original series. That's 1 over n, harmonic, diverges. So nice when we recognize those series, right? And so no for 1. So our interval of convergence here will be -1, comma 1. Now, that's not necessarily true for the integral and the first derivative. Let's see what those series look like. We'll start with the derivative. We'll do letter C first. Okay, this is just another slide. Now we're just going to take the derivative of this general term. So it's going to look like this. N equals 1 to infinity of n to the x, n times x to the n minus 1 over n, because remember we're just differentiating the variable. That was just 1 over n, some sort of coefficient, which is kind of handy because those n's cancel. So this is the series that we are examining from 1 to infinity, x to the n minus 1. Now you can probably see that this term is going to diverge, but remember we are testing a potential interval of convergence -1, 1 based on the original function. Remember it matches, but we do need to test the endpoints in this series to see if the endpoints converge, because this is different than our original function. So let's put -1 in. We get -1 to the n minus 1, which diverges. And then we're going to put +1 in, and we get +1 to the n minus 1, which is just really 1. It diverges as well. So both of these 1 and -1 series diverges when that's all you have. So for the integral, my interval of convergence the derivative, my integral of convergence actually is -1, comma 1. Now let's test it for our last trick will be to do the integral. So we're going to take this term right here and integrate it. Add 1 to the exponent, n plus 1, divide by the new exponent, n plus 1. So this is the general term of the integral of the original function, x to the n plus 1 over the n that was already there times n plus 1. Okay, so again we know that this is the potential interval of convergence. We don't have to find that again. We just need to test the endpoints in our new series and see if they converge. So let's try -1. Putting -1 in for x gives us that alternating term, -1 to the n plus 1, and then what I have left is 1 over, let's distribute this and make it n squared plus n. Now we need to know if this series converges or diverges. Since it's an alternating series, we should probably use the alternating series test. Condition 1, remember, the nth term would have to go to 0, which it does. And then condition 2 would be that each subsequent term, n plus 1, n plus 2, etc., be smaller than the previous one? Well, as you're increasing the denominator, you would be decreasing the fraction, so this does converge by the alternating series test, which means that for this particular function, we have -1 in the interval of convergence. Now, all we have to do now is test +1. So go back to this. It just becomes, we get n equals 1 to infinity. 1 to the n plus 1 is just 1. And then here's our denominator. I'm going to write this as n squared plus n again. We need to know if this series converges. Now, this is an alternating. There's, you kind of run through your mind, probably not going to use the limit test. I guess you could use ratio or root, but what I think of when I see this is comparison. Let me compare this 1 over n squared plus n to a series that I know converges, which is this p series, 1 over n squared. Now, since this series converges, if I can show that term for term my series is smaller, then it must also converge. But notice that adding the n here means that my denominator would be larger, making the fraction smaller. So by the direct comparison test to a convergent p series, I can also say that this series converges. What this tells me now is that +1 is also in the interval of convergence. So for the integral, -1, 1 was the interval. For the derivative, no endpoints were included, and I can't remember the other one, but you get the idea. That's it, boys and girls. But here's your homework slide. Something beautiful for you to look at. Now look at that little whatever you want to call it, piece of artwork, I guess, and the swirls and movement of what you see here is not random or chaotic. It is defined by sort of mathematical pattern. These are fractals, right? So it is just a picture of sort of understanding what beauty really is. We think that, math imposes some sort of rigid form on art, but in fact it underlies it. And so I have this quote from Bertrand Russell for you. Mathematics possesses not only truth but supreme beauty, a beauty cold and austere, like that of sculpture, sublimely pure and capable of a stern perfection such as only the greatest of art can show. That's nice. Now homework, page 666, don't be alarmed. This is not the Antichrist. It's just the page where your homework starts. You're going to do 1 through 4 all, 5, 8, 9, 12 through 21 multiples of 3, 45, 46. I believe this is a record for the longest video that I've created thus far, but boys and girls, it's totally worth it. All good stuff.